This is the first video for section Seqr H. In this video we're looking at mathematical induction. Now to start with I'm going to say that mathematical induction does not occur in any assessment, module tests or progress tests or end of course tests. I don't get too caught up in it, it's exposing you to it. So mathematical induction is a process by which to prove an infinite sequence of statements. The mathematical statements, Mn, are equations that are true for the set of positive integers or natural numbers and are often stated in the form Nn for all positive integers n. Now the general process for mathematical induction is step A, prove Mn is true for the initial integer value, i.e. show that M1 is true. Step B, assume that the statement is true for a general integer k, so assume Mk is true. Step C, show that Mn is true for the k plus 1th integer, so show that Mk plus 1 is true given that Mk is true. It then follows that if the statement is true for the first integer k equals 1, using the third step above leads to the statement being true for the second integer k equals 2, and then if M2 is true, M3 must also be true, etc. More simply, showing M1 to be true implies M2, which in turn implies M3 to be true, and so on for the infinite set of integers. So let's look at an example. This example says prove that 1 plus 2 plus 3 all the way up to n equals n bracket n plus 1 all over 2 for all positive integers. So the first step is to verify the statement is true. So verify true for n equals 1. So for n equals 1, you've got 1 plus 2 plus 3 plus all the way up to n equals n plus 1 all over 2. That's what you're given. Now for n is 1, the left hand side is just going to be 1, your first term. Your right hand side is going to be 1 bracket 1 plus 1 all over 2, which equals 1 times 2 all over 2, which is 1. So therefore left hand side equals right hand side. Statement is true. Okay, so M1 is true. Our next step is to assume true for n equals k. So that means that we've got 1 plus 2 plus 3 plus all the way up to k is going to equal k bracket k plus 1 all over 2. Okay, so assuming Mk is true. Our last step is going to be that we have to show it's true for n equals k plus 1. So we've got 1 plus 2 plus 3 all the way up to k plus k plus 1, because we're going up to the next term, has to equal k plus 1 bracket k plus 1 plus 1 all over 2. And that's k plus 1 all over k plus 2 all over 2. Okay, so that's what we're needing to show. Now what you'll see is our assumption, this here is this here. Okay, so what I can do is take all of this here and plug it in there. Okay, get a pen. So I've got I have k bracket k plus 1 all over 2 plus k plus 1. That's my left hand side. So I've just substituted this in for here. Now let's go to a new page so I don't run out of room. So I've got, let's just rewrite that step. My left hand side is now k bracket k plus 1 all over 2 plus k plus 1. So we don't lose sight, our right hand side was k plus 1, k plus 2 all over 2. So from here, let's get a common denominator of 2. So now I have k bracket k plus 1. This is all over 1, so to get down there I have to multiply it by 2, so plus 2 bracket k plus 1. Let's expand our brackets. K squared plus K plus 2K plus 2 all over 2. Simplify K squared plus 3K plus 2 all over 2. I can now factorise that top to be K plus 1, K plus 2 all over 2, which lo and behold equals my right hand side. So therefore mk plus 1 is true given mk is true. And you can see at the bottom of the page in the textbook it says, as statement is true for n is 1, it must also be true for n is 2, therefore it is true for n equals 2, must be true for n equals 3, and so on. So you could write that out. I really don't want to waste time here, but you can say, to end with, hence 1 plus 2 plus 3 all the way up to n has to equal n plus 1 all over 2 for all positive integers n. Okay? So let's look at the next one. Prove 5 to the n plus 2 bracket 11 to the n is divisible by 3 for all positive integers n. So first step, for n equals 1 in 5 the n plus 2 bracket 11 to the n. Okay, so we have 5 to the 1 plus 2 bracket 11 to the 1, which equals 5 plus 2 times 11, which equals 27. Now 27 equals 3 times 9, so therefore divisible by 3. So therefore m1 is true. Second step. Assume 5 to the k plus 2 bracket 11 to the k is divisible by 3. Okay, so I can write that as 5 to the k plus 2 bracket 11 to the k equals 3m, where m is an integer. Okay, if it has to be divided by 3, then I have to have it as 3m. So therefore, assume m to the k is true. Okay, now I'm going to move on to a new page for step C. So step B was at 5 to the k plus 2 bracket 11 to the k equals 3m. So step C is show that 5 to the k plus 1 plus 2 lots of 11 to the k plus 1 is divisible by 3. Oops. Okay, so I'm starting with 5 to the k plus 1 plus 2 lots of 11 k plus 1. Let's play with this. I can separate the 5 to the k plus 1 to be 5 times 5 to the k, because we just add our indices. Then I can separate what's here to be plus 2 times 11 to the k. Okay, from there I'm trying to make it be a factor of 3. That's what I'm trying to pull out. So I can rewrite the 5 as 11 minus 6. Then that's 5 times 5 to the k, plus, rearranging what I have here, I can have 11 times 2 times 11k. So I just made the order different. Now let's split this up by expanding the brackets. I have 11 times 5 to the k minus 6 times 5 to the k plus 11 times 2 bracket 11 to the k. You can see these 11s happening everywhere, so bring it out the front. I get 5k plus 2 lots of 11 to the k, and then what's left is that minus 6 times 5 to the k. So all I've done is factorise for that 11. Now you should see this here equals that up there. Okay, oops. So you've got all of this here is the same as this up here. So I can now replace that with the 3m. So I have this equals 11 times 3m minus 6 times 5 to the k. Now I can bring a 3 out. Bring the 3 out here, I've left with 11m minus, well, 3 into 6 is 2 times 5 to the k. I have a factor of 3. Okay? I have that factor. So therefore, this is divisible by 3. So m to the k plus 1 is true, given m to the k is true. Finish with hence. 5 to the m plus 2 lots of 11 to the n is divisible by 3 for all positive integers. Okay? Bit tricky, I know, because there's a lot of playing there and you have to try and think about, well, how do I play? How do I get it to be divisible by 3? So it's taking it to a very abstract level, but remember, you're not going to be assessed on this. Okay, my last one, prove the sum of 1 over 2 to the p equals 2 to the n minus 1 all over 2 to the n for all positive integers n, and then I'm given this here. Okay, so step A. For n equals 1. We're given sum of from 1 to n of 1 over 2p equals 2 to the n minus 1 all over 2 to the n. So from there, my left hand side is going to equal just 1 over 2 because we're making that p equal to 1. My right hand side is going to be 2 to the 1 minus 1 all over 2 to the 1, which is simply a half. Left hand side equals right hand side, therefore statement true for M1. Okay, next step. Assume the sum of 1 over 2, oops, that should be a superscript, 1 over 2 to the k equals 2 to the k minus 1 all over 2 to the k. Okay, so we're assuming mk is true. New page. So let's write that assumption down again because we're going to need it. So we're assuming sum 1 over 2k equals 2 to the k minus 1 all over 2 to the k. So my last step is we need to show k plus 1, p equals 1, of 1 over 2 to the p equals 2 to the k plus 1 minus 1 all over 2 to the k plus 1. Let's look at our left hand side. Now, that's simply 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 2 to the k plus 1 over 2 to the k plus 1, if I expanded it out. Now, this here, all of this is this here. Okay, it's the sum of just a k. So I can substitute that. And I end up having 2 to the k minus 1 all over 2 to the k plus 1 over 2 to the k plus 1. Okay, now I'm going to play 2 to the k minus 1 all over 2 to the k equals plus 1 over 2 to the k times 2 to the 1. So I've just split this up into these two. From there, get a common denominator. So I need an extra 2 on this side. That stays the same. So now I have 2 times 2 to the k minus 2, I've just expanded the brackets, plus 1 all over 2 times 2 to the k. That becomes 2 to the k plus 1. We have a same base. Negative 2 plus 1 is minus 1 all over 2 to the k plus 1, which is my right hand side. So I have to finish with a hence statement, but I don't have enough room. So what now? Complete exercise Seqr H1. Again, don't get too caught up in the whole mathematical induction. Try and understand it. Try to see where it's going, especially if you're planning on going into TM2.